Hi all, this is Harvey here. Just real quick here, I just wanted to show you. I wanted to get a handle on the load power for Glenn's recent work. I wanted to see if I could figure out how the phase shift and the inductive impedance might be affecting the output power across the load. So I created a cell calculation. Some of you may recognize this, some of you may not. This is a little more advanced using the R1C1 format of cell referencing. What we have, I don't want to go real deep into this, but I want to show this calculation for those of you that can understand it, and I want to just basically describe what I've done here. In order to allow myself the ability to adjust the phase shift and adjust the inductive impedance and have that relative inside of each cell calculation, it necessitated that I do this. Essentially what I'm doing is I'm taking the voltage that's across the load in order to determine the current that's running through that load. And in order to determine that current, I have to take the voltage across the calculated impedance, which I want to be able to vary. So that's what this last part of this is. I have the 10 ohms of the resistance, which is a known calculated value or calibrated value, and then I have a reference to a cell where I add an arbitrary inductive impedance to see how that affects the outcome. And then I also have the need, within the calculations to take a phase shift. And that's what this indirect and address commands allow me to do, because the address command resolves to a particular reference, in this case R2C6, which is absolute, and that's this cell right here. And what this cell is this is a calculated value of how many rows gives me a particular offset. And it references to a cell down at the bottom of the sheet where I put in the degrees that I want. And so what it does is it takes the degrees that I've specified, divides that by 9, because 90 degrees is just about 10 rows of offset. I could show you that real quick here. We'll look in column 2 and we'll see where we've got column 3 is our channel 2, and we'll see where we have one of our spikes here at 500 volts. And if we count that back in time to see where our current would be, it's going to be just about where this thing levels out. So here we are at the center, at the center of the peak, and we're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see by the time we get to about 10 apart, we're pretty much leveled out. So that's how I came up with a spread of about 10 rows to give me 90 degrees. So it's about 9 degrees per row, which the resolution on that isn't as good as I would like. I could probably redo this in the other files. The 20 microsecond file or the 2 microsecond file will give me a much better resolution on that spread. But at least I wanted to do it here where I have more data to average and get the results. Okay, so what we end up with is we end up with the ability to adjust the phase shift in degrees and to adjust the inductive impedance in ohms to see how it affects our output power. As you can see, I've currently got a 35-degree phase shift. Basically I'm saying that the current is lagging the voltage by 35 degrees here. And that, with a 260 ohm inductive impedance plus the 10 ohms resistance, gives me an output power on the average of very close to what the battery power is. Are we really getting that big of a shift in the current? I don't know. We got to wait for the heat baselines and really do a caloric test on that. But it is interesting to see, how just some small changes in the degrees can affect the power. If we were at 0 degrees, which we know we aren't, and we had no inductive impedance, then we'd have 655 or 652 watts. But we know that we're not at 0 degrees. We know that we're at least 45 degrees, and we know that we have at least 200 ohms of inductive impedance, which puts our output wattage well below our battery wattage in this case. I wish I could say for sure that we're 45 degrees or more. I can't. I don't know what the capacitance is of their resistors that they've handmade, and that affects that phase angle. And I don't know what the inductive impedance is really, because that 209 ohms that I came up with for a total of 219 was based on the frequency of the pulse itself, which is much higher than the rest of the frequency throughout the time period. So the inductive impedance is always changing, and those changes themselves affect how the circuit alters this phase angle. It's very complex. These are very rudimentary treatments to see how it affects it, but I did want to share that with you guys, let you know what I was playing around with to see if I could figure out how the power is being thwarted, I guess would be the proper term, because optimally if we had no inductive impedance and had no phase angle shift, we would have a lot of power to play with. But because those two conditions exist, there we are. So, if you have any questions, go ahead and PM me and I'll see if I can answer your questions. Thanks.